Today's topic is, well, two topics today: Hartree-Fock, or mean field approximation, and theory of screening. And with this discussion, we finish our topic of Giliu model. And starting tomorrow, we moved on to different things. Namely, we start discussing bosonic systems. Hartree-Fock is an extremely useful approximation which is applicable to any interacting system. And basically, the question that one asks is the following. Given a Hamiltonian that has a structure like this, namely there is a term which is non-interacting, like a kinetic energy term, and that we can solve exactly, and then some term that has these four fermion terms, which we don't know how to solve exactly. What is the best Hamiltonian of a non-interacting form that best approximates this full Hamiltonian? Okay. So Hartree-Fock approximation answers this question. Okay, so we want to write a non-interacting Hamiltonian that we denote H with this superscript HF for Hartree-Fock that has basically the same form as this Hamiltonian, but this single particle energy spectrum will be in general different from just a non-interacting single particle spectrum. And the question is, what is the form of that non-interacting single particle spectrum when I write it like this? Okay, so this is what is this? I put a question mark here. We're approximating this full Hamiltonian H with this non-interacting form. And the question is, what is the best function of momentum and potentially spin that I can choose so that this Hamiltonian best approximates the behavior of the full interacting system? That's the question of Hartree-Fock approximation. Now, there's several issues that one wants to answer before moving on. For instance, in principle, here one could write something that does not conserve momentum, something like this: C dagger K minus Q alpha times C K beta. And since this would not be Hermitian, really, one could add Hermitian conjugate. So this would also be a non-interacting problem that we can solve exactly. And so in principle, we could ask for this more general form of this single particle Hamiltonian. However, one could argue that since the full Hamiltonian as written here conserves momentum, which ultimately hails back to translational symmetry in real space, then one might expect that Hartree-Fock, the approximate Hamiltonian, also does so. Now, this sounds like a good argument, but it's not always true, right? If you think about it, the full condensed matter theory of everything that was here on the board on Monday, also, if you look at the full Hamiltonian of nuclei and electrons, that preserves translational symmetry, right? There's no translational symmetry breaking term. Nevertheless, we know that the ground state of that Hamiltonian is a crystal which breaks translation symmetry. So that's a subtle issue. The systems described by translation invariant Hamiltonians can spontaneously break that symmetry, like in a crystal. So in principle, one should maybe look for this more general Hamiltonian, but in a kind of restricted sense, Hartree-Fock just considers this line here. Okay? But it's always good to keep in mind that this is not really the most general form. So as I said, this is extremely useful because typically in high dimensions, like in three-dimensional space, Hartree-Fock type approximations work pretty well. They are actually exact in infinite dimensions. One can show that, but of course we live in three spatial dimensions. They are usually not such a good approximation in 2 dimensions, and they typically fail miserably in 1 dimension. But in 3 dimensions, this is a decent approximation often, and it's extremely useful because it allows us to actually make some statements about the system based on a very simple Hamiltonian. So we can understand its ground state, its excitations pretty well. So what I will do today, I will present a kind of intuitive derivation of this Hartree-Fock approximation. And for those of you who are more rigorously inclined, I will then comment upon how this can be done in a more controlled fashion, although I will not go through all the algebra in the interest of time. Okay, so here's the intuitive derivation. And the intuitive derivation relies on the following observation. Imagine you have 2 operators like this, and you have their product, right? And you should think of this thing as being such a product. Maybe these 2 guys are A, and these 2 guys are B, or these 2 guys are A, and these 2 guys are B. And I can write the following expression, which is actually an identity. Okay, so this is an identity. If you multiply out this term, right, then you find that everything cancels except for A dot B operator. Everything cancels. That's how it's constructed. Okay, so this is an identity, and it's very useful because what one can do, one can argue as follows. Imagine that quantum fluctuations of these operators A and B are relatively small. Namely, so what this is the operator minus its expectation value. So when I say that quantum fluctuations of that operator is small, that means that most of the time this difference is very small because the operator is close to its expectation value, right? If that's the case, then what I have here, I can write this as delta A times delta B. I have a product of 2 such small terms that correspond to small quantum fluctuations. So Hartree-Fock approximation, in some sense, can be thought of as neglecting this term and replacing all such products by this type of expression. Okay? So that's the kind of intuitive hand-waving way of introducing Hartree-Fock. And if you're dissatisfied with this, then just wait 15 minutes or so, and I will tell you about the more systematic way of deriving this. So what we're going to do, we're going to treat the second term in this Hartree-Fock approximation, basically using this what is called Hartree-Fock decoupling of a product of 2 operators. And for this, we have to identify which pairings of these 4 operators we should identify as operators A and B. And according to our previous discussion, there's basically two possible pairings that are expected to give rise to non-vanishing expectation values. And it's these two and these two, like we did on previous occasions. So basically, in one case, we identify this as an A, this as a B. And in the other case, we identify this pair as A and that pair as B. And then we just plow ahead and use this Hartree-Fock decoupling scheme. The only proviso is that when the two operators in each pair are not next to one another, then we have to use commutation relations to bring them together, but we know how to do that. So Hamiltonian, interaction Hamiltonian in the Hartree-Fock approximation accordingly looks like this. And let me just write, and then I comment. So this is the bottom decoupling, okay? And now I'm going to use the top pairing, and here the minus sign comes because I need to perform a one anti-commutator operation to get it into proper form. Okay, and hopefully these last brackets are self-explanatory. They just stand for this term, and I just don't want to write all the C's again. It's clear what is meant by that. Basically, it's just a term like this, but the expectation value is on both terms. Okay, so now what we need to do, we now need to study these expectation values to see if we can simplify them in order to make some progress and simplify this Hamiltonian, which at the moment looks kind of complicated. So let's first look at this one. And again, we did expectation values like this already yesterday. So it should be no surprise that what we find. So basically, since we're looking at a ground state, so we're calculating the expectation value of this in the ground state of this type of single particle Hamiltonian, which will be, again, a Fermi sphere. It's no surprise that the only way this is going to be non-zero is when the electron state that is annihilated by this operator is then recreated by this one. So I have to insist that Q is equal to 0, because only then this is going to be the case. And then my expectation value looks like this. Yes?
When you did the commutation to get the second line,
yes,
you put like a CK alpha past the C minus T.
Yes.
Do you pick up a commutator from the delta function?
Do you pick up some constant term? Okay. Yeah, I think you do not pick up any constant term, and if you do, then it vanishes, because what I'm going to get is the right result. But that's a good question, and I will have to think about that. I don't want to spend half an hour chasing zeros or ones here. Sorry about that. But yeah, I think this is the right result. Yeah, in the first case, basically, I'm just pairing up these two. Once I make an expectation value, then I can commute this through the expectation value. That's fine. When I'm doing these two, it looks like, indeed, I have to commute these two guys across one another. And it looks like there might be something there. But like I said, I have to think about...
So you've got your p's in, like you've got the third term there should be C, K, L.
Yeah. I think that sort of term, yeah, if I commute these two, I would get something when Q is equal to 0, and that term would vanish.
I think the third one should be C, K, alpha, not C, P, alpha.
Yes. Okay, this is P, this is K. Yeah, now it's correct. K plus Q, P minus Q, P, K. Yeah, this is good now.
Should be beta than alpha?
Yes. Okay, now it's good. Any other?
So here you only keep two channels, like the density channel and the n channel. You forget about the two channels, right?
So we're okay. So the question is, why don't we do this pairing here, right? We could, in principle, pair up these two and those two. Now, of course, then we would be looking at an approximation to the Hamiltonian which does not have this form, because, I mean, you know, we could do that, but then we would be looking at an expectation value like this, C dagger, right? And obviously, in this ground state, that expectation value is 0, because it creates two states on top of two electrons on top of some Fermi sphere, and you take an inner product with that same Fermi sphere. So that would vanish, right? So indeed, if we're looking for, and you know, this will come later in the course, for a superconducting state, then we would exactly look at these, what is called anomalous expectation values. But in the simplest, that's what's called Hartree-Fock Bogoliubov approximation. And today we're just studying the normal state, non-superconducting state. So we just restrict our attention to these. Okay, but that's a good question. Yeah.
Can you explain the rationale of spontaneously keeping both channels?
Spontaneous?
Spontaneously keeping both channels. Like actually, the identity there can apply to either channel, right? You can pair up in. And I'm going to comment on that in just a second. Okay. Any other questions? So this is one of the expectation values. Yeah, and this should be a minus sign as well. Sorry, I'm not paying enough attention today, I guess. So let's look at the other channel here. And here we have an expectation value, C dagger P minus Q beta CK alpha. And again, for this expectation value to be non-zero in the ground state of this non-interacting Hamiltonian represented by the Fermi sphere, I have to demand that P minus Q is equal to K, and that alpha is equal to beta. And then again, I have the simple expectation value C dagger K alpha CK alpha. Now, in the literature, this is what is often called direct term, or sometimes Hartree term, and this is what is called exchange or Fock term. Okay? Now, at this level, if you do it like this, in this hand-waving fashion, then it is really not clear whether one should keep both of these or just one or which one. And it turns out that if you do it in this ad hoc manner, then you can conceive of just Hartree approximation, in which you would keep just this first line, and that would be some approximation to this Hamiltonian. Or you could keep just the second line, which would be the Fock approximation, and that would be some approximation to this Hamiltonian. Remember, this is not a rigorous theory that we're developing. It's approximation. That's in the title here. And they both have their merits. However, it turns out that if you do this systematically, namely you really ask this question, what is the best single particle energy here that approximates the Hamiltonian, and you do this, as I will discuss shortly, in a variational sense, then the answer is that you have to keep both of these channels simultaneously. And you can convince yourself of that by just doing this systematically. I don't know of a better reason, but again, one has to keep in mind that either one of these are approximations, and so they both have their merits and their disadvantages. And for instance, we will see that for straight Coulomb interaction, this direct term vanishes exactly, and the only non-zero term is the exchange. For other types of interactions, it may be the other way around, and one just has to use the best approximation available. Any other questions? Okay, so let me just substitute these expressions here and write the full Hamiltonian along with this H0 term. What happens is that the full Hartree-Fock, full Hamiltonian in the Hartree-Fock approximation after this procedure looks like this. It's sum over K alpha. And here I have epsilon naught of K, which is my single particle dispersion relation. And then I have various terms. Okay, so basically, all I did once again, I just substituted these terms into these expectation values, and then in the second term, I had to relabel some. Yes.
What were you saying before about the Hartree time vanishing in the direct electrostatic interactions?
Mm-hmm.
Is that to do with the fact that we set when we were summing up H1 yesterday, we went.
Yes, and again, this is something I will comment on in a second. So there's some massaging involved of the second term. So I relabel the momenta in such a way that I can add up these terms into this form. But this is all just bookkeeping. Basically, what has happened here, I have this factor of 1/2. I have two terms. And so I combine them into one, so I have no factors of 1/2. And this is the result. I'm also neglecting these terms here, which just correspond to some overall constant. They don't have any operator content in them, so there's potentially some overall energy constant that I'm neglecting, but that's fine because I can adjust my zero of energy any which way I want. Now, often, this piece here is called epsilon direct. So this is the so-called direct contribution to the interaction. And as you can see,
this is momentum independent, so this is just some constant, whereas this piece here is called, with the minus sign, epsilon exchange, and this depends on momentum, and sometimes we call these Hartree term, and this one we call Fock term. Okay? So let us now see what the consequence of these corrections are for the Coulomb interaction. Okay, so this is the Coulomb interaction in Fourier space, and we have to remember that for Coulomb we are compelled to skip the q equals 0 term, which simply means that this Hartree term, which contains exactly v at 0 momentum, this will vanish. Okay, so for Coulomb interaction, there's only Fock term. And a Fock term we can now explicitly evaluate. So let us look at minus epsilon exchange at momentum k. So I'm just evaluating this sum. And just remember that this expectation value, this is just a number operator. Expectation value in a Fermi sphere will be that step function as yesterday. So I can rewrite everything like this, 4 pi e squared over v, just putting in the expression for the interaction, sum over p. Here's my step function, pf minus p. That's this expectation value. And then in the denominator, I have p minus k squared. And as usual, I will transform this summation into an integral. So I get 4 pi e squared over 2 pi cubed integral d3p theta pf minus p minus k squared. And this integral, which I continue evaluating up here, can be evaluated by transforming into spherical coordinates with the z-axis aligned with k. So basically, I do this. This is my k vector, and this is my p vector, and this will be the polar angle, which I call theta, and then there will be azimuthal angle, which I call phi. And in that coordinate frame, I can write it like this, e squared over 2 pi squared. I notice that nothing depends on the azimuthal angle, just because this here I will just have a inner product of the two vectors, which will depend on theta, but not on the other angle. So I can right away perform an integral over the azimuthal angle. Then I have the radial integral, and I have the polar angle. And the denominator looks like this. It's p squared plus k squared minus 2pk times cosine of that angle. This thing is basically p dot k that I get when I square the two. right? And this integral actually can be evaluated because I can make a substitution here in the second integral. Z is cosine theta, and this sine theta is exactly the volume element that I need to make this into a simple integral. So I get something like this. And this is an elementary integral. The result will be a log. And you can believe me that I can perform this integral. And I do it like this. It's e squared over k times pi, integral from 0 to pf So this here in brackets is the integral. The integral is this times 1 over p times k. So 1 power of p disappeared and 1 power of k appeared there. And this is also an integral that one can perform analytically. And the result looks like this. Epsilon exchange of k is minus e squared kf over pi 1 plus kf squared minus k squared over 2kf k log of k plus kf divided by k minus kf.
That's the upper bound of the
Well, yeah, so here I'm kind of using kf and pf interchangeably. So pf is equal to kf. Yeah, I guess I started with pf here, but then switched to kf in the last line. But they mean the same. They're just the Fermi momentum. Yes?
So this is true for the ground state. If you wanted to look at like any kind of excited states, you have to.
Yes. So if we want to look at the excited states, then the only change will be that this expectation value is not given by the step function, but it's going to be given by a Fermi-Dirac distribution function. In that case, unfortunately, you cannot really perform these integrals analytically, but you can do some Sommerfeld type approximation for low temperatures, and yeah. So the final result of this can be written as follows. Do I have enough space here? Well, maybe I should use the other blackboard. So the final result for Hartree-Fock in Coulomb potential looks like this. Epsilon k is equal to epsilon naught of k, which is the non-interacting energy. And it can be written economically like this: 2e squared over pi kf times capital F of k over kf, where capital F of x is just that function, written in terms of dimensionless variables, 1/2 plus 1 minus x squared over 4x log 1 plus x 1 minus x. So this is the result. Now let us think about it a little bit. So first of all, let's try to plot this function f, just so that we know what we're dealing with. And this function f has the following behavior. So this is x, this is f of x. And it starts at 1 when x is equal to 0. And then when x is equal to 1, has non-analytic behavior. So basically it looks like this. And here at this point, the wave function has an infinite, the function has an infinite slope. F prime of 1 is minus infinity. So, and this will have some important consequences for the physics of this. So if I plot this epsilon k, so here I'm plotting the energy, and here I'm plotting k over kf. Okay, now I can use the, I will use the colored chalk, good. So if this is the parabola, just h bar squared k squared over 2m, the free electron gas, then this, so this is 1. Then this Hartree-Fock corrected energy looks something like this. Okay. This is roughly -2. This is -1. And what I'm plotting here is E over the Fermi energy. So for non-interacting, this will be +1, and so on. It turns out that, so basically if you want to fill this, if you want to put in the same number of electrons as you started with in the non-interacting system, then all these states here will be filled. So these states are all filled up to the Fermi momentum, okay? And it is precisely this point here that corresponds to this point on this function. So here, the dispersion has infinite slope. So this guy here, of course, what I'm plotting here, this is the full epsilon k, whereas this one is the non-interacting one. And at this point here, epsilon k has infinite slope. An infinite slope at the Fermi level, that's a very bad thing, right? Among other things, that implies that the Fermi velocity is infinite. It implies that the density of states goes to 0. And you will get to explore some other consequences of this property in the tutorial and in the next assignment. So this is actually a major failure of this Hartree-Fock approximation for Coulomb interacting electrons. So this implies divergent Fermi velocity Vf is basically d epsilon decay. So when the slope diverges, this is divergent. It also implies vanishing density of states. Which would imply that you don't have any specific heat in this type of weird metal. So all these are just, I put just exclamation marks. These are kind of failures of this approximation, quite severe failures actually. So what's wrong? How can one repair this approximation? Well, if you trace this failure or these problems back where they occur here, they actually arise from the long-range nature of the Coulomb potential. If you were to screen the Coulomb potential so that it's not so long-ranged in real space, then these problems would all go away. And again, this is something that you will be asked to show in your next assignment. So let me just write that. Now, remember in the previous lecture, I wrote down this expansion on the blackboard of the ground state energy in powers of Rs, and I showed you that one term has this extra log in it, and in principle, the coefficient just diverges if calculated without that log. And the reason for that is precisely the same thing as here. So if one puts into these calculations just an unscreened long-range Coulomb interaction, then one gets into all these troubles. And it is precisely these facts that motivate the theory of screening. And that's going to be our next topic. So basically, this is how the development here proceeds. You study the system, you make certain approximations that look reasonable, but then at some point, inevitably, you come to these contradictions. Basically, you find these behaviors in approximations that just disagree with experimental data. Right? We don't really in metals see divergent Fermi velocity, or we don't see zero density of states at the Fermi level. So then you ask, well, what went wrong? And you go back and you identify the problem, and then you try to repair it. And in this case, the fix comes through the theory of screening. So I asked you to go over 2 pages of general theory of screening from Ashcroft and Mermin. And I hope you did. I'm just going to very briefly review what's done in those 2 pages, and then I'm going to do a calculation of the dielectric constant that enters screening theory and susceptibility. So basically, what this theory of screening does, we consider a metal with electrons in it, and we put in a test charge, let's say positive test charge, and this test charge will attract a cloud of electrons to it, so that on long length scales, you just don't see that charge. If you were to put an observer here, it would not see that positive charge because it has been screened by this. And it is useful to introduce 2 quantities, which is phi external, which is just the potential produced by this charge in the absence of screening, and then phi total, which is the total electric potential when you include screening. And it turns out that in momentum space, the two are related as follows. Phi q is related by 1 over epsilon q phi external q, where epsilon is the dielectric momentum-dependent dielectric constant in the material. And another important quantity here is the charge that is induced by this perturbation, which is also related to the total potential now through the susceptibility function. Like this. And so this is dielectric constant, this is susceptibility. And one can show that there is a very simple relation between the two, namely epsilon q can be expressed as 1 minus 4 pi over q squared times chi of q. And this, in turn, from this equation is 1 minus 4 pi over q squared rho induced q divided by phi over q. And let me put a box around it. And there's nothing that goes into it other than classical electrostatics, right? And we're going to use this. Basically, the way we're going to proceed is as follows. This chi here is a quantity that is easy to compute from condensed matter physics, because what one can compute, as we will see, is a response of a system in terms of the charge induced by the potential, right? That's a quantity that one can easily calculate. The quantity that one actually wants to describe a solid is this dielectric constant, but as we see, it's very simply related to chi of q that we will be able to calculate. So are there any questions about this? So we're going to calculate this susceptibility in two distinct approximations. Each has its own merits. In the literature, there's actually many different, increasingly sophisticated approximations that are employed to calculate these properties. We will just limit ourselves to the two simplest ones that are kind of instructive. So the first of these is the so-called Thomas-Fermi approximation. Sometimes also called semiclassical approximation, as we will see in a moment. And it proceeds as follows. So we take Hamiltonian of non-interacting electrons. In second quantization, it's written like this. And so we're neglecting interactions here. Now, this is kind of a funny thing. So although we're neglecting interactions at this level of the Hamiltonian, electrostatic interactions are actually put in at this level, right? The fact that, for instance, we have this 1 over q squared, that's because we're assuming that these charges here are interacting electrostatically. This 4 pi over q squared is the electrostatic potential. So basically what we're doing, we're treating this non-interacting part of the system quantum mechanically, but the interactions are being treated classically at the just electrostatic level. Nevertheless, this is an extremely successful approximation. and it reveals the nature of screening very nicely. So what we take for our single body Hamiltonian is just the usual non-interacting piece, Laplace squared over 2m, and with a minus sign, I guess, and we add to it phi of x, which is the local potential at some point in the material, which is due to all the other electrons plus our test charge. Okay? Now, we notice the following thing. So if this is arbitrary, this phi, then of course we cannot solve this problem, because if this varies in space, then no analytic solutions are possible. However, we notice that for phi of x equals phi naught, and this is constant, the problem is very easily solvable, right? This is just a problem in a uniform potential, and that constant doesn't really do anything. So in that case, we can immediately go to momentum space and write our Hamiltonian like this. It's just sum over k. And notice that I'm neglecting spin here. Just to make things simpler, I'm neglecting spin. Spin up and spin down behave in the same way here. I just add some factors of 2 at the end. I don't want to clutter the notation. So we neglect interactions and spin here. Spin is completely inert in this theory. So this is a first quantized, second quantized Hamiltonian in momentum space. It's just non-interacting fermions, and you can view this piece here as a chemical potential piece. So we can solve this exactly, and there is no issue there. In other words, we can find wave function, spectrum, everything about this Hamiltonian. Okay, so now here's the gist of the Thomas-Fermi approximation. What they say is that for slowly varying phi of x, we can replace epsilon k that we would put in here with epsilon k of r, and for some reason I'm transitioning in my notes from x to r. So forgive me for this. I'm doing that. And this epsilon k of r is simply h bar squared k squared over 2m minus e of phi of r. Okay? So now this is like semiclassical, or what people call WKBJ approximation in quantum mechanics, that you at the same when potentials are varying sufficiently slowly in real space, you can approximately specify both momentum and position in your quantum mechanical wave function, and this is a reasonable approximation. So basically, what we say is that at each point in space, the spectrum looks like this as a function of momentum, but then there's a constant offset which might depend on where you are in space. Now, of course, this is not exact solution, but it's a semi-classical approximation. So what we want now, we want to calculate this epsilon here. And for that, what we need is electron density, right? So let's calculate electron density. And what I'm going to do first, I'm going to calculate the full electron density, and then I'm going to identify the part of it that's been induced by the extra charge that creates this variation in the potential. So electron density can be written like this. It's electron charge times the number density. And as we discussed previously, number density is given by the expectation value of the density operator. And then I write these field operators in terms of CKs. And what results is the following. It's sum over K prime, expectation value of psi star K R. So these are now the single electron wave functions, K prime R, C dagger K, CK prime. And these are just wave functions. So the expectation value is basically just acting on this electron creation and annihilation operators. So I can rewrite this immediately as minus E sum over K prime psi K star R psi K prime R. And this is the expectation value CK dagger CK prime. Okay? And what this is, again, we had this already many times. This is only non-zero when CK, when K is equal to K prime. And let's just be slightly more general here. Instead of working at T equals 0, Thomas-Fermi approximation is usually formulated at non-zero temperature. So instead of a step function, I write here Thomas-Fermi, I write here Fermi-Dirac distribution function, which I call F. So, yes.
Working in like finite temperature here, you also like if you want finite temperature, that expectation value is not necessarily 0 in K prime. It doesn't care. It's the band. So you're making the assumption.
No. So I'm not. Yeah. So the momentum still has to be conserved, right? Even in thermal state, the momentum is still conserved. It's just that the population of individual states is not just sharp Fermi sphere, but it's a bit blurred. So in other words, there is with some probability, you have states above the Fermi level that are occupied, and with some probability, you have some empty states below the Fermi level. Any other questions? Okay, so when I put everything together, then I can write this density as a function of R in Thomas-Fermi approximation as sum over K. You can perform summation over K prime using this, this Kronecker delta. And then the wave function is psi K of R squared, expectation value, times F of epsilon K of R. And so if I'm in just working in a box of some large size, then my wave functions here are plane waves. So for plane wave functions, psi K of R is just 1 over square root of volume times e to minus I K dotted into R. So the modulus squared is just 1. So it turns out this density is actually extremely simple. It's minus E times over volume times sum over K of F epsilon K of R. And here I can even write the Fermi-Dirac distribution explicitly. E over V, sum over K, 1 over E to beta, epsilon K of R minus mu plus 1, where beta is 1 over kBt, as usual. Okay? So let me move on to this side of the board. Okay, so now I have my full density, but what I really want is this density induced by charge fluctuations. So let me define the following quantity. And this is a quantity that I will use to do this, and not function of mu, and its integral d3k over 4 pi cubed times 1 over e to beta h bar squared k squared over 2m minus mu plus 1. So this quantity looks just like this thing here, except I have converted the summation into integral. That's why I have this. And instead of writing epsilon k of r, I'm writing just the free particle dispersion. And this is useful because in this notation, I can write my induced charge density as rho induced of R as minus E, which I keep in front of everything, and naught of mu plus E phi of R minus and naught of mu. Okay? So you recognize this expression here as being my actual charge density that I have calculated here, right? That expression is exactly the same as this one, just remembering that this epsilon k is h bar squared k squared over 2m minus E phi. So I tack it to the chemical potential so that I can use that expression, whereas the second term is simply n naught at mu, which is the charge density of a uniform system. If I, okay, let me raise this for you. So that you can see better. So this is just the charge density of the uniform system when this phi of r is vanishing. Okay? So the induced charge density is just the difference between the actual density of state, actual density of charge that is produced by this potential minus the uniform density. Okay? Any questions about this? So now I will make a further assumption. I will make an assumption that E times phi r is small compared to mu. And it's obvious why. When this is small compared to mu, then I can expand this expression to leading order in small phi, and I can simplify it. This assumption is really not necessary, but if I want to push this a little farther analytically, then I have to make that assumption. In this case, I can write rho induced of r as minus e squared d n naught d mu times phi of r. And this is an important relation, because if I look at this expression here, I see that that identifies the susceptibility, because susceptibility chi, according to the definition, is just the constant of proportionality between the induced charge and the total potential. So from here, I can identify chi of q is minus e squared d n naught over d mu. And this is independent of q. So in the simplest approximation, we find that susceptibility is just a number which is given by the first derivative of the electron density of a uniform system with respect to the chemical potential, and it's momentum independent.
And to get that, you explicitly prove both sides.
Yes, okay, yeah. So both sides, obviously, since this is Q independent, I can just Fourier transform them and get that relation. Yeah, that's a good point. If this was, if there was a more complicated relation, then I could get something that is momentum dependent. Okay, so now I can use my relation between susceptibility and dielectric constant to express the dielectric constant. Epsilon q is 1 plus 4 pi e squared over q squared dn naught over d mu. And let me put a frame around this. Often one defines a Thomas-Fermi wave vector by the following relation: k Thomas-Fermi squared is 4 pi e squared dn naught over d mu. And this has a good property that with this definition, this a dielectric constant becomes quite simple. Like this. Okay, so this needs to be dimensionless by definition, and so whatever else is here aside from momentum has to combine to give me some momentum scale, and so I can as well write it like so. Okay. So let us now do an example. So we did this fairly abstract calculation, but how does this translate? It came from me forgetting to put another line there. Thank you. So example, a point charge. How does the point charge that I insert into a metal get screened in Thomas-Fermi approximation? So for a point charge, I have my external potential given by some charge q divided by r, right? If I just stick in a positive point charge, or, well, just charge q point charge, then the potential will just be a Coulomb potential. And if I Fourier transform this in momentum space, this just becomes 4 pi capital Q over Q squared. We see this. And once I have this, I can use the general relation written up there, the first line under the word screening, between the total potential and the external potential to calculate what the total potential will be. And I need to do that in momentum space. So this is just 1 over epsilon q times phi external of q. And now I just substitute this expression that I obtained from Thomas-Fermi approximation, and I substitute this expression for the potential. And you can see right away what happens. This becomes 4 pi q divided by q squared plus k squared Thomas-Fermi. Okay? So in momentum space, the effect of screening is to replace this denominator here that is 1 over q squared with something that cuts off at the momentum scale that is small compared to Thomas-Fermi, right? So something that is singular when q goes to 0 to something that is finite. In other words, you can see right away that in real space, what corresponds to small q is long wavelengths. So this potential will be decaying much faster at long distances in real space, right? So you can see right away that this is actually corresponds to screening. One can see this explicitly by performing the requisite Fourier transform. Namely, if I calculate the Fourier transform of this, e to the I q dot r of this potential, I will not do the integral explicitly for you, but it can be performed rather easily if you wanted to. And it's q over r times e to minus r times k Thomas-Fermi. So this is the screened Coulomb as we know it. Or sometimes called Yukawa. Potential, if we identify k Thomas-Fermi with 1 over mu. Sorry, no, just with mu. Yeah. Remember, in our calculation initially of a Coulomb of a Gillieu model, we use this potential, but instead of KTF, we use the parameter mu here, which we then send to 0. But now we see that actually, when one considers screening, the same type of screened Coulomb potential arises in the simplest approximation due to Thomas and Fermi. Any questions about that? Yes?
In other approximations, you always get an exponential decay?
No, you don't get always an exponential decay. In other approximations, you can get other behaviors, and that's why I'm going to show you another approach to this, which is the so-called Lindhard approximation, and it's valid in a different regime. Okay, any other questions?
So is this better in the long run?
So, okay. So this is valid. The Thomas-Fermi approximation is valid when this potential varies slowly in space. That's the nature of the semiclassical approximation. In addition, in order to get to this analytic form, we had to assume that this potential is small to compared to this mu. And obviously, in this example, both of these approximations break very close to the origin, because there, this potential is neither small nor does it vary slowly, which means that very close to the origin, one cannot really take this literally. On the other hand, if you look at this result, the strongest effect of this added exponential term is when r is large, right? When r is small, this exponential term just goes to goes to 1. So there's nothing much being done to this potential, whereas the strongest effect is when r is large, because then you have a difference between 1 over r and exponential decay, which is a huge difference. And that's where, so in the regime of large r, both of these conditions are satisfied, right? So we're good here. Okay, so as the last thing today, we consider what is called the Lindhard approximation. If I can find it here.
Is this also RPA?
Pardon me?
Is this RPA?
No, this is RPA.
Like
The Lindhard approximation is also called the random phase approximation. The Lindhard dielectric function. So this is obviously due to Lindhard, who first calculated this dielectric function, but is also in the literature sometimes called random phase approximation. And the rationale for this second name will not be obvious from the calculation that we do today. It's obvious when you do this in a diagrammatic language, where basically you're summing some classes of diagrams and you neglect those that appear to have some oscillating phases in front of them. They would be difficult to sum for other reasons, but you say that they probably sum to 0 or something negligible because their phase oscillates, whereas you just retain those diagrams that have all positive sign. So that's the nature of this name, but that's not going to be obvious at all in this approach. I'm just mentioning it for historical accuracy. So the approximation that we make here, or that Lindhard made, simply assumes that this potential is small. It's a small perturbation. And treat it in perturbation theory. So unlike Thomas-Fermi, we're not really making any assumption about how slow or fast it varies. It can vary as slow or fast as you want, but it has to be small so that you can treat it in perturbation theory. And then it's basically a standard perturbative calculation. So this is our Hamiltonian. And we take this term to be our unperturbed piece, and the second term we take to be our perturbation. And what we want, once again, we want to calculate charge density to leading order in perturbation theory. Okay, so rho r in leading order of the perturbation theory. And for this, where is my expression for rho r? Rho r is up there. That remains valid. so what we need is that wave function, right? We're going to calculate that wave function psi in first order perturbation theory. And for this, I just use the usual perturbation expansion that hopefully everybody remembers from their quantum mechanics. So the wave function is the unperturbed wave function plus the first order perturbation. And the first order perturbation for the wave function looks like this. I have energy denominator. And I have to calculate the matrix element of my perturbation. And my perturbation H prime is just this. And I'm missing my E here. And this is psi k 0 and psi k 0 of R. So this is the first order perturbation in the wave function, where psi naught of k is just the solution of the unperturbed Hamiltonian, namely the plane wave, and everything else should be obvious. This is just the spectrum of the unperturbed Hamiltonian, which is just a quadratic spectrum in momenta. So let me write those things down. Psi k naught of R is just 1 over v squared e to the I k dot R, and epsilon k naught is h bar squared k squared over 2m, and it holds that h naught psi k naught is equal to a k naught psi k naught. Okay, so all I need to do is to calculate this matrix element, and then from that evaluate the charge density. And let's see if I can do that in the remaining 10 minutes, because I would like to finish this today. So the matrix element looks like this. So I'm just, by definition, writing this matrix element as an integral over space, and I put in the explicit form of these wave functions. And if I look at this, I see that this is nothing but the Fourier transform of this potential phi at wave vector k prime minus k. So I just note that. And of course, I'm using here a confusing notation where I distinguish the function in real space from its Fourier transform simply by writing the argument as either R or K, but hopefully nobody will get confused by that. So the wave function then is simply as follows. Psi k of R is approximately to first order psi k naught of R minus E over V sum over k prime. I just put this a matrix element here, k minus k prime, divided by epsilon k naught minus epsilon k prime naught times psi k prime naught of R. So now it's time to write the expression for the density. And the density rho of R, just as we had before, is minus E sum over K psi K R squared times f of k. Now I'm abbreviating this f of k Fermi-Dirac distribution function. This is just f of epsilon of k. And now remember, I'm not doing Thomas-Fermi anymore, so this epsilon k is just does not depend on space anymore. It's just the usual k squared dispersion. So now imagine what I need to do, right? I need to evaluate this, and the wave function is given right up there. So I take this expression and plug it in, but I'm only interested in this expression up to first order in my perturbation, right? So I will have 4 terms, but one of them will have 2 of these guys, and I will just neglect that term. So I just write the leading term unperturbed plus the first order perturbation. So I can write this as follows. It's minus e. And here I will get sum over k, f of k, psi k naught squared. So this I get from this term times its complex conjugate. So this is the unperturbed term. And then I get a cross term, this times that, plus the complex conjugate. And it has the following form: sum over k, fk, psi k naught, sum over k prime, psi naught k prime, divided by epsilon k naught minus epsilon naught k prime, phi k minus k prime. And I get a similar term, just complex conjugated. Here this thing needs to be complex conjugated. Okay. So this first piece here, quite obviously, is my rho naught of R. This is just the density of the unperturbed system. And this whole thing here is my rho induced. And this is what I'm interested in, right? Once again, I want to identify how rho induced depends on my potential so that I can extract chi and from that epsilon. Questions? No questions. Good. So let me just continue. So just focusing on this piece, what I'm going to do, I'm going to put in the explicit form for these wave functions as well as the energies that are listed up there. And what I obtain is the following: rho induced of R is then minus e squared over v sum k prime. I have 2 summations here. I have f of k e to the I r k minus k prime divided by epsilon naught k minus epsilon k prime 0 phi k minus k prime plus complex conjugate. Now it's just massaging these terms to some more convenient form. So I perform a substitution. I go from k and k prime into k plus 1/2 q and k, capital K, this is capital K, minus 1/2 q. It's like going to a center of mass coordinate system. And with these, yeah, it's just a simple algebra that anybody can do. I can combine this term and its complex conjugate, and the result looks like this. Minus e squared over v, sum on q, e to the I r dot q, sum over k, f k plus a half q minus f k minus a half q epsilon naught k plus a half q minus epsilon naught k minus a half q. Okay, so if you look now at this expression, what this is saying is that basically I'm performing a Fourier transform into real space of this expression. So what this must be my chi of q, right? So if I were to go to Fourier space on the left-hand side, then I would find here rho of q, and it's this times my phi of q, so the constant of proportionality as before, I identify as chi of q. And let me just record that result. So in Lindhard approximation, and this is the famous Lindhard formula that you find in many textbooks, or RPA formula if you wish. Random phase approximation is sum over k, fk plus aq minus fk minus half aq divided by h bar squared k squared, sorry, k dot q over m. And let me put a box around it. So this is a Lindhard dielectric function. Okay, so yeah, let me ask Dennis. I have maybe another 5 to 7 minutes, and I could finish this, or I can just stop now and postpone until tomorrow. So should I?
It's 12:22. I think that it's better to stop.
Okay, good. So basically, what we'll do next, I was hoping to finish this, but let me not keep you too long. We will basically analyze this form.
How long will it take?
Well, it would take me 5 to 10 minutes, so let's just postpone until tomorrow. We will basically analyze this form next time, and we will show that. Yeah, we will show how.
It's quite complicated.
Yeah, we will show how in a certain limit it reverts back to Thomas-Fermi, but there's also some new physics in this form that we want to explore. Okay, so thank you very much, and I see you back here tomorrow.